In this final part of the lesson, we're going to do some more problem solving with mixtures and solutions. So the first thing we're going to talk about is the fundamental concept of mixing it up in mixture problems, and then we'll just work a couple of examples. So let's start with the big idea that's going to be lurking behind all of these problems. A 20-ounce bottle of fruit drink contains 15% pure fruit juice. How much pure fruit juice is in the beverage? Well, really the question here is, what is 15% of 20 ounces? And to calculate this, we're just going to multiply 20 ounces by 0.15. And let's see, I need to know 15% of 20 ounces. Well, I know 10% of 20 ounces is 2 ounces, and another 5% would be another ounce. So this will be 3 ounces. So to answer the question, there are only 3 ounces of pure fruit juice in 20 ounces of a fruit drink. So when we were thinking about this problem, there were two quantities to consider: the amount of pure juice and the total amount of the beverage, which in this case was a mixture of pure juice and water, maybe some corn syrup, maybe some other stuff. What we did know for sure is that was 15% pure juice. In mixture problems, we're typically asked to mix two solutions in order to achieve a desired result. A solution contains a certain amount of pure substance. It might be juice, salt, acid, alcohol, and a bunch of water thrown in, or maybe some corn syrup. The amount of pure substance and the amount of solution will be two distinct quantities in the problem. So when we're working these mixture problems, we want to keep the amount of solution separate from the amount of pure stuff. Let's look at an example of mixture, and we're going to start with just juice. Dina mixes 20 ounces of the 15% fruit drink with 12 ounces of another beverage that is 75% fruit juice. What is the final mixture? What percent of the final mixture is pure fruit juice? I'm going to start with understanding the problem. Dina's beverage should end up being between 15% and 75% pure juice. The 15% fruit drink is probably going to end up diluting the 75% fruit drink. We have the information we need to calculate the amount of pure juice in Dina's mix. We know how much pure juice was in the 15% juice drink. We can figure out how much pure juice is in the 75% juice drink, and that will tell us how much pure juice we have. We also know that Dina's going to end up with 32 ounces of her juice mix, 20 ounces of one type, 12 ounces of the other. We can use the ratio of the amount of pure fruit juice to the amount of her mix to calculate the final percentage, or the percent of pure fruit juice in her beverage. So let's do it. So we want to know what is 15% of 20. So calculating 15% of 20 ounces, that's what the amount of pure fruit juice coming out of the 15% fruit juice drink. That's going to be 3 ounces of pure fruit juice in that beverage. Now she also has 12 ounces of juice, which is 75% pure fruit juice. So 75% of 12 ounces is 9 ounces. 75% is just 3/4. 3/4 of 12 is 9. So altogether, there are 12 ounces of pure fruit juice in her mix. So we have 12 ounces of pure fruit juice, and altogether there's 32 ounces of fruit drink, and we want to calculate this percentage. So to find this as a percent, I'm just going to divide 32 into 12. So 12 divided by 32, that's going to be 0.375. Now as a percent, that's 37.5%. So Dina's mix is 37.5% pure fruit juice. Now let me say a little bit about this. We mixed a 15% fruit drink with a 75% fruit drink. And when we mixed them up, we didn't end up with a fruit drink that was 90%. The percents don't add. We ended up with something in between, 37.5% pure fruit juice. So when we're working these problems, we can't add percentages. It's not going to be quite that easy. But it's not going to be that difficult either, as long as we keep the quantity of pure stuff, like juice, separate from the amount of solution, or in this case, fruit drink. So let's work some mixture problems. We're going to review the problem-solving steps we use when working these types of applications. We want to start by understanding the problem. This is always the most crucial step. We want to clearly define a variable to represent the unknown quantity and write expressions for the other quantities in the problem in terms of this variable. We want to write an equation to model the problem. We want to solve the equation and check the solution in the context of the problem. And finally, state a conclusion to the problem. So let's begin with this example. The shelves in a local pharmacy stock 15% alcohol solution and 20% alcohol solution, but no 17% solution, which is what Marcus needs for his chemistry project. So he's got to mix the 15% and 20% solution together. And we want to know how many ounces of the 15% alcohol solution must be mixed with 4 ounces of 20% solution to make a 17% alcohol solution. So first we have to understand the problem. And with problems like this, it's really useful to organize your information in a table. So I have a table here, and we have got 3 different solutions in this problem. We have 15% solution, which we're mixing with 20% solution, and mixing the 15% solution with a 20% solution will dilute the 20% solution down to a 17% solution. I have 2 columns here, one representing the amount of solution and the other representing the amount of the pure stuff, in this case, pure alcohol. So I'm going to fill in what I know. So for the percent column, I'm just going to rewrite my percents in decimal form, because that's what I'm going to need to use to make some calculations. I know I have 4 ounces of the 20% solution. So if I find 20% of 4 ounces, that will tell me the amount of pure alcohol in the 20% solution. And that is 0.8. So we have 0.8 of an ounce of pure alcohol in the 20% solution. What we don't know is how much of the 15% solution he needs to mix with the 20% solution. So I'm just going to call that X because that's my unknown. Now, how much do we end up with altogether? Well, if I add the amount of 15% solution to the amount of 20% solution, that should tell me the total amount of solution that I have. So this is going to be X plus 4. So X plus 4 equals X plus 4. I'm summing up the amounts of solution. Now let's think about the amount of pure alcohol. Well, if I have X ounces of 15% solution, then 15% of that is pure alcohol. And if I have X plus 4 ounces of 17% solution, then 17% of that is pure alcohol. So I've organized this information. Another thing that I see here is that if I add up the pure alcohol in the first bottle with the pure alcohol in the second bottle, that should equal the amount of pure alcohol in the mix. So what I have here is I've repeated the last column of my table because that's where all the useful information is. So now I want to clearly define my variable and write an equation that's going to help me answer this question. So I'm going to start by letting X represent the amount of 15% alcohol solution. So I also have another expression in my problem in terms of X. That's X plus 4. What does X plus 4 represent? Well, that represents the final amount of 17% solution. So then X plus 4 represents the amount, and I'm measuring amounts in this problem in ounces, of 17% solution. Now, when we made the table to try to understand the problem, we observed that the amount of pure alcohol in the 15% solution plus the amount of pure alcohol in the 20% solution had to sum up to the amount of pure alcohol in the final mix. That's our equation. So our equation is 0.15x plus 0.2 times 4. We already determined that was 0.8 of an ounce. That has to equal 0.17 times the quantity X plus 4. We now have an equation that we can solve. So our equation is 0.15x plus 0.8 equals 0.17 times the quantity X plus 4. So I'm going to start by using the distributive property on the right so I can ultimately combine like terms. So I have 0.17 times X, and let's see, 4 times 17, that's 68, so this is 0.68. That equals 0.15x plus 0.8. Now I want to combine terms so that my variable terms are on one side, all my constants are on the other. So I'm going to subtract 0.15x from both sides of the equation. So on the right, I have 0.02x plus 0.68, and on the left I have just 0.8. Subtracting 0.68 from both sides, I have, let's see, 80 minus 68, that's 12. So that's 0.12 equals 0.02x. Dividing both sides of my equation by 0.02. Let's see, 2 goes into 12 6 times, so 0.02 goes into 0.12 6 times as well. So I end up with the equation 6 equals x, or x equals 6. What was x? This is the amount of 15% solution. So Marcus is mixing 6 ounces of the 15% solution with 4 ounces of 20% solution to end up with 10 ounces of 17% solution. Now we want to check this equation in the context of the problem. And for these checks, we're going to ask ourselves 3 questions. We need to know the total amount of resulting solution. We need to know how much alcohol is in the solution. And our check's going to be, what is the percent strength of the final solution? So the total amount of resulting solution is going to be 6 ounces, that's the amount of 15% solution, plus 4 ounces, that's the amount of 20% solution. So altogether, we have 10 ounces of solution. How much alcohol is in the solution? Well, we need to calculate 15% of 6 ounces plus 20% of 4 ounces to figure out the amount of pure alcohol in the solution. So doing this calculation, I have 15% of 6 ounces plus 20% of 4 ounces. That equals 1.7 ounces of pure alcohol in the solution. Now I need to check out the percent strength. So I need to divide the 1.7 ounces of pure alcohol by the 10 ounces of solution I ended up with. And notice what I have here, if I look at just the numbers, if I multiply both the numerator and denominator by 10, this is equivalent to 17 over 100, which is indeed 17%, which is exactly what I wanted. So I know my solution checks. Now I want to state a conclusion. Remember what Marcus was trying to do. He was trying to end up with 17% solution by mixing 15% solution with 20% solution. So what we just found out is that Marcus needs 6 ounces of 15% solution to mix with 4 ounces of 20% solution to end up with a 17% solution. That wasn't too bad. Let's try another one. So Marcus is back at it again. But now he needs 45 milliliters of a 24% saline solution. So of course he goes to the shelves of the chemistry lab and he only finds 12% solution and 30% solution. And he needs 24% solution. So the question is, how many milliliters of 12% solution and 30% solution should he mix together to get the 45 milliliters of 24% solution that he needs? So we're going to do the same thing again and understand this problem by creating a table to help us organize our information. So now this table looks very similar to the table before, except now we're looking at amounts of pure salt rather than amounts of alcohol. So let's put the information that we know into our table. We know that Marcus needs 45 milliliters of the 24% solution. What we don't know is how much 12% solution and how much 30% solution he has to mix up. So let's think about that in just a minute. First thing I want to do is just fill in the percents, because this column is easy. I'm just writing the decimal forms of the percent here. So let's think about the amount of solution. Let's suppose that Marcus needs Y milliliters of the 12% solution. So I'm just going to put a Y there. That's an unknown. Now the amount of 30% solution is unknown as well, but we do know that we need to end up with 45 milliliters. So the amount of 30% solution we need is going to be 45 milliliters minus the Y milliliters of 12% solution. Notice that the amounts of solutions add. Y plus 45 minus Y equals 45. Now let's think about the amount of pure salt. We have 12% of Y milliliters coming from the 12% solution, 30% of 45 minus Y milliliters of the 30% solution, and 24% of 45 milliliters of the 24% solution. So now let's define a variable and write an equation to solve the problem. So I'm going to let Y represent the amount, and we're measuring amounts in milliliters in this problem, of 12% saline solution. So then 45 minus Y represents the amount of 30% saline solution. And this is also in milliliters. Now, just like with the alcohol solutions, we know that the amount of pure salt in the 12% solution plus the amount of pure salt in the 30% solution should equal the amount of pure salt in the 24% solution. So now we have an equation that we can solve. So first thing I'm going to do is combine like terms on the left-hand side of my equation. And I'll need to distribute first. So since I have a few computations here, I'll pull out my calculator. I need to calculate 30% of 45. That is 13.5. So I have 13.5 minus 0.3y. And I also need 24% of 45. That's 10.8. So combining like terms on the left-hand side, 0.12 minus 0.3 is negative 0.18. Subtracting 13.5 from both sides of the equation leaves me with negative 0.18y equals, let's see, 10.8 minus 13.5, that's 2.3, negative 2.3, negative 2.7. Should have pulled my calculator out for that one. Now dividing both sides of the equation by negative 0.18, this time I am going to pull my calculator out just in case. So I'm dividing 2.7 by 0.18. I know a negative number divided by negative is positive, so that will work. And I end up with the equivalent equation, y equals 15. So what does this mean? Marcus needs 15 milliliters of the 12% solution, which he's going to end up mixing with 30 milliliters of the 30% solution. Let's check to make sure we end up with a 24% solution. So we're going to ask, what is the total amount of resulting solution? Well, we know that already. We were told it had to be 45 milliliters. And we need to figure out how much salt is in the solution. So I'm going to calculate 12% of the 15 milliliters plus 30% of the 30 milliliters to figure out the total amount of salt in the solution. So I have 12% of 15 plus 30% of 30, that equals 10.8. Finally, I have to check the percent strength of the solution. So I'm looking at 10.8 milliliters of pure salt to the 45 milliliters of solution. And when I calculate this ratio, I should end up with the percent that of 24%. So 10.8 divided by 45 equals 0.24, which is indeed 24%. So everything checks. So what can Marcus do now? Marcus can mix 15 milliliters of 12% solution with 30 milliliters of 30% solution to obtain 45 milliliters of a 24% solution. Now we just have time for one more example. We're going to work through it kind of quickly because you'll see fairly quickly that this example is just like the problem we just did, except now we're not going to think about chemistry anymore. We're going to think about chocolate. A bakery wants to use chocolate with 20% fat content. They have low-fat chocolate that is only 12% fat and creamy edible chocolate that is 50% fat. How much of the two types of chocolate should they use to create 50 ounces of a chocolate that is only 20% fat? So to understand the problem, we want to ask, have I solved a similar problem before? Well, really, this is exactly the same problem Marcus had in the chemistry lab when he couldn't find the percent of saline solution that he needed. So we can start by creating a table. And we know that we want to end up with 50 ounces of the moderate fat content chocolate. What we don't know is how much 12% low-fat chocolate we should mix with high-fat chocolate. So you can see this table is exactly like the table we created for Marcus. If we look at the amount of pure fat in this case, in all of the three cases, and we add up the pure fat in the low-fat and high-fat chocolate, that will be the amount of pure fat. We're going to end up in the 50 ounces of the 20% fat chocolate. So now I'm just going to write out a solution rather quickly, but I'm just going to write it out from start to finish. So I'm going to let C represent the amount, and we're measuring amounts in this problem in ounces, of low-fat chocolate. Then 50 minus C is the amount of, well, high-fat, maybe good chocolate. So now that I've defined my variables, I can write an equation. So I'm going to add up the fat content, the amount of pure fat in the low-fat chocolate and the high-fat chocolate, and that should equal the total amount of fat in 50 ounces of 20% fat chocolate, which is 10 ounces of pure fat in the mix. Now I can set out to solve the equation. So 0.12C plus, let's see, 50% of 50 is 25, minus 0.5C equals 10. Combining like terms on the left leaves me with negative 0.38C plus 25 equals 10. Now I need to continue on a new sheet of paper. So subtracting 25 from both sides of the equation, I have negative 0.38C equals negative 15. Dividing both sides by negative 0.38 should tell me the amount of low-fat chocolate I need in the final mix. So 15 divided by 0.38, both numbers are negative, so the result will be positive, gives me about 39.5 ounces. So I'm going to round this off to 39.5. So now I need to check my solution. So I'm just going to do a calculation here. I am going to add up the amount of fat in the final mix and divide it by the 50 ounces that I have. And I'm just going to do a quick calculator check here on my calculator. So I have 12% chocolate, and I have 39.5 ounces of that. So that's 4.74 ounces of pure fat in that. The remaining chocolate is high-fat chocolate, and that's going to be about 10.5 ounces of that chocolate. So I need to add in 50% of 10.5. So altogether I have about 10 ounces of fat in this mix. Now I need to divide this number by the total amount I have, and this is 0.1998, which is about 20%, which is exactly what I want. Now I rounded off my result for C, which is why it didn't come out to be exactly 20%. So now I can state a conclusion. The bakery needs to mix 39.5 ounces of low-fat chocolate with 10.5 ounces of high-fat chocolate to end up with 50 ounces of chocolate that is only 20% fat. So there we go. We've worked several examples of mixture problems, and they're not that difficult as long as you remember to keep the amount of pure stuff like juice, alcohol, salt, or fat separated from the amount of solution. Just keep your information straight in a table. The equations are really easy to write, and you're done.